Thank you for tuning in to my webinar on making waste heat useful for decarbonization. In the past, we talked about the subject of heat recovery as some way to get a return on investment. But now, with decarbonization being a point of focus, heat recovery is going to become even more important, as it has the potential to greatly offset carbon emissions in commercial and residential buildings. So for those who haven't realized yet, Canada is a very cold climate. The vast majority of energy use in the building is from space heating, second only to water heating. Over half of the energy used is for space heating. Typically about a third is used for ventilation. So in this webinar we're going to talk about heat recovery for ventilation. We're going to talk about heat recovery for the internal space heating as well, and how it can help with decarbonization. The research, for example, in Toronto shows that 52% of the greenhouse gas emissions come from homes and buildings. And this is mostly from burning gas to heat indoor spaces. So where can I find waste heat in the building? The first area we're going to look at is in the ventilation system. We bring in fresh air into a building or process. We have to exhaust a similar amount of air from that building. And so is there an opportunity to recover the energy between the two airstreams? The second part is recovering energy within the building. Buildings, primarily larger ones, will have multiple zones, and some zones may be in cooling and some zones may be in heating. So is there an opportunity to recuperate the heat between different zones of the building to reduce our heating load? So what are some of the obstacles of heat recovery, and why isn't it implemented as often as it should be? The first is you might have intermittent simultaneous loads. In order to do heat recovery, you need what is called a simultaneous load, heating and cooling happening at the same time, so we can exchange that energy between the heating and cooling load. So what do we do about loads that are intermittent? The other issue is that a lot of HVAC equipment available cannot develop the required temperature that can be useful for the application. A lot of buildings need up to 180-degree hot water supply in the middle of winter, and the technology might not be there to develop that amount of heat reliably, especially from cold sources. These systems sometimes, especially when retrofitted into buildings, require additional equipment, machinery, piping, and systems, and this becomes complicated. And so that generates a lot of apprehension. And lastly, when we implement these physical systems, we also need control sequences to control them. Often these can exist as very simple standalone controls, but sometimes when you integrate with larger building systems, you also need to integrate with a control sequence to ensure that the heat recovery equipment isn't going to fight against some of the existing equipment that's providing heating and cooling to the building in the first place. So first we're going to talk about the heat recovery opportunities that exist on the ventilation side, or the air-to-air side. And many of us will be familiar with what I will call passive heat recovery devices. These might be heat wheels, heat plates, or heat pipes. And that's where the air is brought over an area that's in close proximity, so we can exchange heat energy between your supply and exhaust air streams. And here's an example where we're bringing fresh air of -20 over a heat rotor and partially heating it up with some return air that's brought back at room temperature, or 20 degrees. And in these examples, you're going to need some kind of top-up heat energy, where we still have to typically burn fossil fuels to bring that remaining amount of air back up to a room neutral condition, or room temperature condition. Active heat recovery, on the other hand, can extract a little bit more heat energy from these air streams, and that proves to be useful for decarbonization. An active heat recovery, unlike a passive device, is going to use a compressor or refrigeration system to extract that additional heat energy. So what this looks like is return air coming over our cooling coil or evaporator coil in this case, and our compressor is going to suck out that heat energy and dump it into the condenser or heating coil. That return air, or air from the building, which is waste air, is cooled substantially more than it would be in a passive heat recovery device. Therefore, we have more heat available. So we can bring in our fresh air at -20, for example, and now we're able to heat that fresh air all the way up to 20 degrees or room neutral without any top-up heat energy. Active heat recovery can also be used in a form in which hot water is generated from this waste exhaust airstream. In a similar fashion, the return air is going to be brought over the refrigeration system, where it will cool that exhaust air again to a very low temperature to extract as much heat as possible. The compressor is going to dump this heat this time not in an airstream but into a water-cooled condenser where hot water can be produced. The major advantage of this system is when we talk about decarbonization, is we can now use our exhaust air as the source of decarbonization. As soon as we make hot water, we can use this heat in every part of the building. We can use it in the ventilation air, we can use it for space heating, perimeter heating, radiant heating, and we can also use it to generate domestic hot water if we so choose. So this means that our ventilation system and the heat recovered from our ventilation system can now be used to offset carbon emissions in other parts of the building. And because active heat recovery can extract so much more heat using the compressor, we're going to have excess heat left over from the ventilation that can be then used to contribute space heating and domestic hot water. And as it becomes more mild outside, that means that we're going to have even more surplus heat available from this machine to further contribute and offload the carbon emissions from our base building heating system. This is not achievable with typical passive heat recovery devices, in where they can only heat the incoming ventilation air. They're not able to heat other building spaces, and certainly not able to heat domestic hot water. So what does this mean for total operating costs? So in this example, we're using Ontario gas and electric data to generate an example of a 10,000 CFM ventilation system. This might be characteristic of a 20-story office or apartment building. So the blue indicates the direct fuel cost, and the orange indicates a carbon tax added to that fuel. So if we were to heat that with straight up natural gas, it would cost $47,000. If we were to heat the same airstream with electricity, it would be $82,000. Then we have gas plus a 70% effective passive heat recovery device. This might be a heat wheel, for example, $14,000. Electric plus the same passive energy recovery device, $24,000. An air source heat pump, which could be used to generate hot water and then taking that hot water to heat the ventilation air, $42,000. And then active heat recovery at just over $3,000. You can see there is a substantial reduction in the operating costs in active heat recovery that mainly stems from the extremely high coefficient of performance, or COP, you get from using exhaust air as a source. And then how does this example shake out in terms of carbon emissions? This is using the carbon intensity of the Ontario electric grid, which is relatively clean. So natural gas is over 144 kilograms, electricity 25,000 kilograms, and then we have gas plus heat recovery, electric plus heat recovery, passive devices. Air source heat pump is similar to using an electric element plus a heat recovery device, and then we have active heat recovery. Again, the lowest carbon impact device when compared to all other types of heat recovery. So we've discussed heat recovery in the ventilation air, and now we're going to move on to talk about heat recovery internal to the building. So to better understand the concept of simultaneous loads and where they may take effect, so I want you to think of a very small building or perhaps even a detached house where we have one zone. There might be people and computers and lights inside this building, and they are generating heat. And we're talking from a cold climate point of view here, so it is very cold outside, it's winter time. These devices, or the internal heat load, is not sufficient to heat the space. We have a tremendous amount of heat loss to the outdoors, and so we have to burn some kind of fuel in order to maintain this zone. This zone is in heating mode. So now let's think of a larger building, such as an office tower or shopping mall. We'll have an interior zone, which is shown by the dark gray square, and this might have people and computers and lights, again generating heat. And then we're going to have a zone around the perimeter. And just like before, it's very cold outside, so we will have heat transfer from this perimeter zone to the outside. So to make up that heat transfer, this zone must be in heating mode. We have to be adding heat to the perimeter in order to offset the heat loss through the envelope of the building. However, on the inside of the building, in the core zone, the computers, people, light bulbs are generating too much heat, and where I've shown this orange X, there is no heat transfer from the core zone to the perimeter zone. This is because, in theory, the HVAC system is keeping the core zone at the same temperature as the perimeter zone. I mean, it generally, as you walk through an office building, doesn't get colder and colder and colder as you approach the perimeter. Perhaps if there's substantial drafts around the perimeter of the facade, but in theory there's no heat transfer. So this interior zone is generating heat, but there's no way for it to exit through the envelope. So this zone actually requires cooling. And this is where you have an instance in which you are simultaneously heating the perimeter of the building and cooling the interior of the building. And so is there an opportunity to recover the heat between the two zones so we're not burning gas to heat the perimeter while running an electric chiller to cool the interior? And if you don't believe this phenomenon happens frequently, I'd encourage you to look up into the sky on a cold winter night. You'll often see steam coming from the top of many buildings, and some of the steam comes from the boiler exhaust, but a lot of it is from cooling tower use in the middle of winter. And this cooling tower use is because electric chillers, electric water-cooled chillers, are being used to cool the core, and then some kind of heating system is being used to heat the perimeter. So recovering that heat internal to the building can yield significant reduction in carbon emissions. So what does this look like in an example? So here we have an electric chiller cooling a 100-ton cooling load, rejecting that heat to a cooling tower. Simultaneously, we have a gas boiler generating 1.7 million BTUs of heat to service a heating load. So in this example, the chiller is using, for example, 75 kilowatts of electric input. We have an electric pump and electric cooling tower fans, and the boiler is simultaneously using 56 cubic meters an hour of natural gas. So what if we used the waste heat from the chiller to serve this heating load of 1.7 million BTUs? Well, in this example, we're able to shut off the cooling tower for this simultaneous load, and we're able to shut off the boiler or greatly reduce its use by 1.7 million BTUs. And we're going to use perhaps a more specialized heat recovery chiller to do this load. That heat recovery chiller will consume a little bit more electricity. We've gone from 75 kilowatts to 144 kilowatts. We've shut off the pump to the cooling tower. We've shut off the cooling tower itself, and we've shut off the boiler. So in this equilibrium condition, we get a 28% reduction in operating costs, which is fantastic, but we also get a 95% reduction in carbon emissions for this load. And this is where heat recovery can play a huge role when it comes to reducing carbon emissions in existing buildings. So using this graph to visually represent what will happen, you can see I've represented the cooling load with the blue line and the heating load with the red line. In the center of the graph, this would be the summer, and on the edges of the graph would be the winter. So let's assume we have a 500-ton peak cooling load. We have a 100-ton cooling load in winter that represents the cooling load of those core zones. And we have kind of an equilibrium point where heating and cooling loads are roughly equal, and that occurs in the shoulder season at around 200 tons. So what ends up happening here is the area I've shaded in blue is a potential energy for heat recovery. This can be achieved completely with the heat recovery chiller or heat recovery unit, and there's no need to burn any new fuel in order to meet this heating demand. So sizing the heat recovery chiller for a 200-ton peak, which is the equilibrium in this case, might have the greatest impact, the greatest carbon emissions. The most cost-efficient way to do this would be to size the chiller for a 100-ton load. That would be represented by this blue shaded area. And in this example, that chiller would run 24/7 to get you the most cost-efficient solution, and that's equivalent to a almost $60,000 annual savings, which is fantastic for a 100-ton machine. And put in perspective, it's equivalent to the peak heating load of about 12 detached houses that would be removed completely from the system. So again, heat recovery can have a tremendous impact when we're talking about decarbonization. Thank you for watching this short webinar. If you found the content useful, make sure you like, also subscribe to hear more about my decarbonization and electrification ideas for cold climates. Heat recovery is a technology that's been around for a very, very long time, and it's underutilized. Traditionally, we thought of it as a return on investment, but now with the decarbonization effort, it's really going to be playing a very critical role in reducing the carbon emissions in new and existing buildings.